Okay, we are in the month of February, our second month of the year 2016. We are continuing to do quantum mechanics. Here's the outline for today. We're going to spend some time on new material, but we're also going to take some time to answer any questions that you may have as you've started to dig into this take-home exam with all these quantum problems. So I'm going to leave a generous part of the hour for us to discuss those questions that undoubtedly you are starting to have. Now, a few more things on particle and a ring, and then we're going to do particle on a sphere. So, we've been talking about particle on a ring. We got the boundary conditions, the cyclic boundary conditions, and those led us to the wave functions for particle on a ring. Psi m sub l of phi, where m sub l is the quantum number, and we found out that this wave function is 1 over the square root of 2 pi e to the I m sub l of phi. M sub l, again, being that rotational quantum number that takes on the values 0, plus or minus 1, plus or minus 2, and so forth. So, normalized wave function is this, and now if we apply the Hamiltonian to this particle on a ring case to this wave function, we'll find that we get the particle on a ring energy levels. So let's quickly do this. This is minus h bar squared over 2 times the moment of inertia. Let's see. D squared, d phi squared. Strictly speaking, I should probably have straight d's rather than curved d's, but we'll, for the moment, leave it this way. And then we're going against our wave function e to the I m sub l of phi. And the idea is, when I take the derivative, and by the way, I in this case is the mass of the particle times the radius at which it is cycling around there, squared. So we take the second derivative of this, and we get h bar squared over 2i, and then inside this we get 1 over the square root of 2 pi, and then we get minus I m sub l squared e to the I m sub l of phi. Now, convince yourselves I did this right. I'm taking the second phi derivative, so we get an I m sub l coming out once, we get an I m sub l coming out twice, and so minus I times minus I is minus 1, so this is minus m sub l squared when you work this all out. And then let me use another color here. We'll use light blue here. All of this is just psi m sub L of phi. So what I have is in rearranged form, this is h bar squared over 2I. Oh, and this should have been a minus in this part. Make sure you pick up those minuses right here for the energy term. So it's minus h bar squared over 2I times the quantity minus m sub L squared times the wave function back again. Let me get this other marker a little bit darker. So just kind of rearranging it. 1 over 2 pi e to the I m sub L phi. Now, there's a reason why I'm doing this. This is psi m sub L of phi. And I'm going to contend that all of this is E m sub L. And I'm going to also say that all of this equals the Hamiltonian in terms of phi, and obviously this is the wave function psi m sub L phi. So just see what I'm doing? I'm showing you that these are all the pieces, right? Here's the H, this is the E, and here's a psi, and here's a psi together. And this E m sub L, let's bring it around like this. This E m sub L, therefore, is going to equal h bar squared m sub L squared over 2I, or h bar squared m sub L squared over the mass times the radius squared of this circular orbit. So we basically we've taken Schrodinger's equation, h psi equals e psi, and we've done the derivatives, and we can actually see all the pieces laid out very nicely. Okay? Now, can we use other operators besides the Hamiltonian? Remember, the Hamiltonian is the total energy operator. It gives you the total energy of your system. Can we use another operator than a Hamiltonian to probe other properties? The answer is yes. Okay, this is just one of many quantum operators. We could choose an unbelievable assortment, millions of quantum operators, and we would come to the end of it. But I'm going to choose a special one. I'm going to choose the operator LZ. And this is the angular momentum operator about z-axis, unit vector I. Okay, this is LZ. And what does this operator look like? It's kind of interesting. It is simply h bar divided by I d p phi. Not a second derivative, but a first derivative. Okay? So let's form the relationship LZ of phi acting on psi m sub L of phi. So we write that all out as h bar over I d phi 1 over the square root of 2 pi e to the I m sub L phi. So we're going to take the derivative of that, and we're going to get h bar over I.
Professor, you're going to trip over that chair sooner or later.
Here, there we go. You're probably right. Okay, so I'm going to pull out an I m sub L, like that, and I'm going to get the wave function back again. Do you buy that?
Mm-hmm.
Okay, notice the two i's cancel out, and we get the very powerful result and very relevant for chemistry and atomic physics, that the value that has remained is h bar times the m sub L quantum number. And notice, so this is the quantized angular momentum. And by the way, you can check this out. H bar has the units of angular momentum. And this makes sense. The higher the m sub L quantum number gets, the bigger it gets, the faster, in a crude picture, the faster the electron is whizzing around in this circular track, and the more angular momentum it has about the z-axis, okay? So h bar has angular momentum units. M sub L is just an integer. And now, in the angular momentum case, it matters whether we're going clockwise or counterclockwise. M sub L will either be a positive or a negative number, and so our angular momentum will turn out to be positive or negative. So it turns out that this h bar m sub L is the angular momentum eigenvalue. This is it. So we've proven we have a relationship LZ of phi psi m sub L of phi equals h bar m sub L psi m sub L of phi. It's the same form as Schrodinger's equation. This is the angular momentum eigenvalue, h bar m sub L. Notice for the energy, the energy has m sub L going in as the square. We don't care whether it's spinning around clockwise or counterclockwise for the energy. But for the angular momentum, it does matter because there is a direction to the angular momentum. Okay. We've pretty much now done particle on a ring. Just another thing, a ring. Okay. Oh no, my dear, how about a sphere?
I keep going online and I keep seeing particle in a ring. It's the same thing, right?
Yeah.
Because I'm thinking in a ring, it's like in the ring.
Well, I mean,
on a ring, it's like only on the.
Okay, you can imagine a tiny little tube with a BB going around in this tiny little tube.
Got you. Okay.
Okay. And there's various ways we could envision it.
Okay, gotcha.
Okay.
I was just making sure there's no distinction between the two.
No, I don't think so. Now, we've done particle in a box, we've done particle on a ring, and we've seen examples downstairs at the lab of both. The cyanine dyes kind of model particle in a box. All our cyclic aromatic hydrocarbons model particle on a ring. And we have talked about molecular vibrations where you have a Hooke's law spring. We haven't done the spectra on those yet. We're going to wait for our new infrared unit to come in, which should be in any day, by the way. But an obvious extension of particle on a ring is to do particle on a sphere.
Yep.
And I've given you the other logical case for an exam question, particle on a cylinder.
Which is basically
Which
like,
you break it's the product really of particle in a box and particle on a ring. You kind of put those together, you'll get those. But we're going to do particle on a sphere because this is an incredibly important and practical case. Particle on a ring is important, but particle on a sphere is super important. It's great to have all these things on the computer and on the TV so that we can go back and see these details.
yeah, definitely.
Okay. So now we go to the critically important case of particle on a sphere. So let's draw a coordinate system with both Cartesian and spherical polar coordinates. So we'll have the three unit vectors in the Cartesian system, I, j, and k, in the usual fashion. We'll have a sphere centered at the origin of radius r. And we'll think of a point on the surface of the sphere that looks like this. Let me get it all drawn out. So this is a point r, theta, and phi. So we can have an r here. This is our phi angle in the xy plane, and the theta angle down like this. And we're going to do fixed radius. R equals capital R. And we're going to confine the particle to the surface of the sphere. Okay. So little r has to be big R. V equals V of r theta phi equals 0. And if r is unequal to big R, V of r theta and phi is infinity. You can't get off the surface of the sphere. And this is true for all theta and phi. So you can have any theta and any phi you want Okay? So those are our conditions for the potential particle on a sphere. So basically we're going to have a Hamiltonian, h, that's a function of two coordinates, the theta coordinate and the phi coordinate. Our wave functions are going to have two quantum numbers, L and m sub L, and they will be functions of theta and phi. And then we'll have energies that are, at least in principle, L and m sub L, times our wave function psi L m sub L, theta and phi. So this is what we're looking for. So this is a two-dimensional quantum problem. Now, we're going to look up, yeah, by the way, you can do this with spherical polar coordinates and throw out all the things where r varies. So it's very easy to do. It's standard calculus 3 stuff. The Schrödinger equation for spherical polar coordinates with theta and phi is as follows. Okay. H of theta and phi, fixed r, is going to take on the values 1 over that fixed r squared, 1 over capital R squared. We'll just say that's fixed. 1 over capital R squared and there's a term lambda squared theta and phi. And it turns out that lambda squared of theta and phi equals 1 over sine squared theta second derivative with respect to phi plus 1 over sine theta d theta of the quantity sine theta times d theta. That's what that lambda squared equals, all of this. Okay, so if we were going to write out the Hamiltonian for a sphere, it would be, wow, it'd be 1 over r squared, let's see if I can do this, 1 over r squared times the quantity sine squared theta d squared d phi squared, and now I'll put in psi L m sub L of theta phi right there, plus the second term, which is 1 over sine squared theta right here, d theta, box goes sine theta, d theta, and we put the wave function back in, psi L m sub L of theta and phi.
What's up with the LML? Sub L, M sub L?
Two quantum numbers. The L. Do you remember the quantum numbers that you learned, the L and the M sub L quantum numbers? Good question. So they're exactly what the L and M sub L quantum numbers are when you learn about the quantum numbers of atomic species in the periodic table, like hydrogen, helium, neon, lead, you know, anything in the periodic table. Those are the quantum numbers we know and love. Okay. Now let's see if I did this correctly. I think I left off, in fact I know I left off a term. Let me just, oh, okay. So the term I left out in this is minus h bar squared over 2m. So in this h of theta phi, there should be an h bar squared over 2m multiplying the 1 over r squared lambda squared. We've said what lambda is, so there's again the h bar squared over 2m r squared, and there should also be a negative sign in front of this. So I've written down now what h of theta phi is when it acts on this wave function. We have all these sine squared thetas and stuff. That's pretty nasty looking, isn't it?
Why isn't that whole, for lambda squared, why isn't that whole thing squared?
Because the lambda squared indicates that they're second derivatives.
Okay, so...
It's not a simple square.
Okay.
Okay, good question though. Now, so that's what the left-hand side of this is h psi, and then we get equals E L M sub L psi L M sub L of theta and phi. Now, a couple of things we want to do, and then we want to start throwing the floor open for take-home exam questions. But the couple of things we want to do is talk about boundary conditions. We're going to have, for theta and phi, there are going to be some boundary conditions. That have to do with the symmetry of the problem. And we'll have ones where the wave function at phi will be the same as the wave function, and fixed theta will be the same as phi plus 2 pi. In other words, it's kind of a generalization of particle on a ring. I can go all the way around in the sphere now. So we'll have some boundary conditions on theta and phi. So psi m sub L of theta phi has to equal psi L m sub L of theta plus 2 pi. Oh, excuse me, phi plus 2 pi. Theta phi plus 2 pi. So we'll have the same boundary condition for phi as we had particle on a ring. And the theta only goes from 0 to pi. And there's some restrictions on theta as well. We'll just kind of leave those implicit at this point. And you can read about figure 831 on page C Fig 831 on those cyclic boundary conditions. Let me just read what our book says. The wave function of a this is figure 831. The wave function of a particle on the surface of a sphere must satisfy two cyclic boundary conditions. This requirement leads to two quantum numbers for its state of angular momentum. So the m sub L quantum number comes from the theta condition, or the phi condition, excuse me, and the L quantum number comes from applying the cyclic boundary condition to theta. Now, at this point, I'm not going to go into the details of the derivation of those cyclic boundary conditions. What I want to do is look at the energy levels. And it turns out the energy levels for a particle on a sphere are E, L, m sub L, and they're as follows. L times L plus 1 h bar squared over 2I. L equals 0, 1, 2, 3, and so forth. Now, I want you to notice something. Do the quantum energies of a particle in a sphere depend on the m sub L quantum number? I don't see any m sub L's there. So it only depends on the theta value, not the phi value. The only time you get an m sub L dependence is when you add something like a magnetic field. But that's a different Hamiltonian if you add a magnetic field to it. So for a particle in a sphere, without an external magnetic field, the energy levels depend only on the L quantum number, not the m sub L quantum number. Kind of interesting. Well, that, in a nutshell, is particle on a sphere. When we add one other key insight, okay? And the other key insight is as follows. Functions that do all this, the wave functions that do this, are called the spherical harmonic functions. They are the functions of spherical symmetry. And they have both a theta and a phi component. Now, aren't you lucky? There is a whole table of spherical harmonic functions. Let's see if I can find the table with those listed. Oh, you know what? That may be in the next chapter. Hold on just a second. Let's see where those spherical harmonic guys are. table 8.2. Let me go back. Oh, there they are. So these are the spherical harmonic functions, C, table 8.2. The page number for that very important table is 311. Now, you've seen the spherical harmonics before. Now, throw away all your knowledge of quantum mechanics, and out of all the pictures on these two pages, which one looks like an s orbital? Yeah, all these. Okay, so here's one right here. Forget the donut. What does that one look like?
P.
What's this next one look like?
D.
And what's the next one with 3 rolls of jelly fat in the mid-six? F orbitals. What would a G orbital look like?
You never mess with those.
Yeah. I would have 3 little.
It'd have 3 little annuli around the middle. And in principle, you can have G, H, I, J, K, L, M, N, O. Yeah, they can go on and on and on. Now, the circular, the ones that look like donuts and martini glasses are actually combinations of px and py orbitals. So the spherical harmonics are the s, p, d, and f orbitals you know and love, or linear combinations thereof. So we've now gotten to this point of introducing the famous spherical harmonic functions. And the reason why we use s, p, d, and f orbitals for all the atoms is we have spherical atoms, right? And for spherical symmetry, you use spherical polar coordinates, and you use spherical harmonic functions as wave functions for the angular description of particles on a sphere. Whether it's a rigid sphere like you're going to do, or whether it's a multi-layer sphere like a multi-electron atom with electrons whirling around at various radii. Pretty cool stuff. And by the way, do we treat the 3, in atomic hydrogen, the 2s and the 3 2p orbitals, 2px, 2py, 2pz, are all at the same energy? That's the L equals 2 quantum energy. Excuse me, L equals 1. Quantum energy. Okay, now, are you going to get all of this in one quick fire hose blast? No. So I don't know how you take it, but either the good news or the bad news is that we'll come back and back and back and back again and again and again to the spherical harmonic functions throughout the remainder of the course, because they capture the symmetry of atoms and orbitals in atoms.
As confusing as this is, it's kind of nice that we're only messing with a Hamiltonian or a wave function, and it's just kind of like different. It's different equations, but it's kind of primarily the same thing.
That's a good insight. We have a Hamiltonian.
Although I still have no idea, really.
And we have and you know, after totally taking this course, you'll kind of be ready to struggle with a beginning class in grad school. You know what I mean? That's how involved it is. I mean, there's just no way out of it. All right. So we, however, at this point want to kind of get away from, we're essentially at the end of the chapter. There's some more stuff we can talk about, but we're essentially at the end. What we want to do is shift our focus from the chapter materials as promised to kind of a look at where you are with the take-home exam, what you might need to go ahead and get it finished and turned in. And that goes for you too, Phoebe.
much, me and Si, we're gonna meet up this week and go over some stuff, but how much did you get done, Si?
I haven't done any.
Okay, that makes me feel better.
Okay, so, there's this.
Can we just, I mean, I read it. Me and Si are gonna meet up and go over it, but do you think we can maybe just go over an actual real problem with real...
What?
Wait, hold on a second. Let me see. Okay. I'm sorry, I'm embarrassed.
And I don't
I should have attempted all of them already.
I didn't even know where to start on something.
Well, this is kind of like getting the whole book of the Kama Sutra and saying, I've got to work through them all before I to fully understand this. And you're tired after the first 3 positions. You should probably cut that out of the video.
I got you, don't worry.
Yeah, right. Go away, dear, I'd rather sleep.
I have a question for you for our. I'm sorry. It's kind of like it's for our lab that we have. Is that okay?
Just throw them at me.
All right. Let me pull it up real quick.
Now, you can see how important the lab is in this course because we're actually probing quantum mechanical behavior.
Definitely. Okay, so for the lab, I felt like there was a lot of derivations that you were showing us. Well, I don't want to mess with that. But at the same time, I feel like I didn't really use any of them. I just skipped to the very end, and I wasn't sure if I'm missing something.
What allows you to skip to the very end?
Because I just looked at the last equation, and it only wants the mass of the electron and Planck's constant.
Okay.
Let me show you. So, I don't know if I'm missing something here.
Oh, is this?
This was the
this
first
is the
lab.
handout.
Mm-hmm.
So this isn't.
This right here. All I did was go straight to here, and by the way, it was really far off from what we got. Because I plugged in,
Isn't that the second lab where we got with benzene and all that?
or is this the second lab? Sorry,
Yeah,
I'm
it's
getting
the second
confused with the labs.
What? Okay. Which? Okay. What? This is the lab where we have the linear dyes, the
Yeah,
colored dyes.
yeah, the color dyes.
Is that the one you want to talk about, or do you want to talk about the benzene lab?
Did I pull out the wrong one? All right, sorry. Give me 1 second. Shoot. Si, do you have that lab on you?
No, no.
Damn it.
Okay. So we don't have the.
It doesn't matter. Even for this one though, my
Well, I mean, you
my
go-
answers were really far off from what we were finding from the spectrometer, what it was giving us. Like, I was getting like, these are what the equation gave me.
Oh, okay, that's the first one. That's the first lab.
Yeah,
Okay.
and all right, never mind. Give me 1 second.
Because these aren't wavelengths that you have here.
No, I know, I screwed that up. Give me 1 second. I have to have it in here. I got like 700 something for what was it, like 570 for benzene?
Yeah, and it's supposed to be like 260. so we need the spectrophotometers at 212.
Sorry, just ignore me. I don't know. I was off on like one of the problems when we would do the equation. It would be from what we got on the spectrometer. It was like 300 nanometers off.
No, there's some.
Is that just something wrong?
There's something wrong. You've got the data. You're either analyzing the data the wrong way or plotting
Yeah.
it the wrong way.
Okay.
Because historically the dye lab has given values very, very close when you go through all the approximations in that handout.
The dye lab, I got close numbers. It's just like for benzene and all that.
Sorry, I wasn't talking about the dye lab. Yeah, it's the benzene.
Okay, so the dye lab
That one.
sounds like that worked out pretty well.
Yeah.
Okay, now the one, you're asking about the one, do you know what that symbol is?
That's the Mexico flag.
It's a Z symbol.
Um,
You know what? You know what's interesting? The Native American, my previous university was Eastern New Mexico University,
oh yeah.
and that was our, the symbol was all over campus.
Yeah.
But they have gone away from the symbol because it's kind of encroaching on the Native American heritage, and so they kind of voted, we really shouldn't be using this anymore.
Yeah. It's definitely a lot
But I
different.
said, what is this? Yeah. What's that have to do with
Sorry, Professor. So I was plugging in for. Actually, I ended up just doing particle in a box. You know, you were telling us that we were able to just use this equation, right?
Okay, this is the box equation.
Yeah. Weren't we able to just use the box equation?
No, you have to use the circle equation, which. Okay, so the particle. So we just did this, right?
Yeah.
The particle in a ring, E m sub L equals m sub L squared h bar squared over 2I. Okay, we just had that on the board.
Yeah.
Okay. Now, right here I'd say, the moment of inertia is really, I convert from h bar to h, so I put a 2 pi down there.
Mm-hmm.
And then the moment of inertia is just the mass of the electron times the radius squared. So if you have a benzene ring, effectively there's a radius r.
Yeah.
And what I say right here is I suck the. Okay, let's see what I do. Did I mess up here? I could easily have done that. Okay, 2 pi r squared. This is really, I take this denominator and I say this is m sub L squared h squared over 2 times 2 pi squared m(e)r squared. This is the moment of inertia. This is just h bar equals h over 2 pi, so I put that in there. I identify this. I get this. Now, the next step is to say, hey, this is m sub L squared h squared over 2 times the mass of the electron times 2 pi times the fixed radius squared. And this is m sub e, okay? So from here to here, there's a 2 m sub e, that comes out. There's a 2 pi squared, and there's an r squared. But this is the circumference of the outer ring.
Yep.
So C is the circumference of the electron orbit in the cyclic pi system. Okay. So this equals m sub L squared H squared over 2m sub E C squared. By the way, I can write all this myself without looking at other books. So do you want to know where I got this? Right out of here. Okay.
I just use particle in a box. Am I not allowed to? I thought I read that in there. I was able to.
Yeah, you have the ring. Okay, well,
We're as far as finding the wavelength, isn't it using that equality where E equals whatever it is in there, and solving for the wavelength?
okay, now, this C is the circumference of the circle, and I say this is the number of,
Times the distance.
the number of carbon atoms times the carbon-carbon bond distance
Okay.
to go around your ring. That's the circumference. But it's the number of atoms times RCC. So you get m sub L squared H squared over 2m sub E.
So basically, you could just do this. You could solve for changing E, find change in E, and then Planck's constant, and you could just solve for, and then solve for
Yeah,
The
I
wave
like
function,
to
right?
set those two equal to each other and then solve for the wavelength.
Okay.
I solve for
Now-
change of E. Well, it kind of looks crazy, but
Now the one thing I wanted you to do, you actually did in lab.
I didn't even mess with any of that.
But that's the whole point.
Okay.
This is a quantum system, and the excitation wavelength is directly proportional to the square. And you proved that for 3 of them. You got a beautiful straight line. In other words, that kind of says the overall model is capturing some significant part of the quantum mechanics. Okay?
So what do you do from that model? How could you plug it into that?
Okay, now, what you could do,
Like with any information from the graph?
okay, the information from the graph, you plot delta E 0, 1 versus 1 over C squared. And therefore lambda is proportional to C squared. That's what you plotted.
Okay.
Because HC over lambda equals delta E. Now, you may not get the exact answer that we get, but the key thing I wanted you to see, and we saw it beautifully, was that the total circumference length squared is proportional to the wavelength.
Okay.
Okay.
So I got 5 something. I got 538. So is that close enough to the 200 because that's what we got for benzene.
Okay. Here's a case where where having them all follow as in a quadratic form
Yeah.
is one thing versus getting the exact right number is another thing.
Okay.
The quadratic form says that this 1 over the size squared dependence holds, but it may not hold treating this as a perfect ring.
Okay.
We might have to have, in other words, there might have to be some distortion parameter. From equation 3, it can be seen that the photon excitation energy is inversely proportional to the square of the box length. That's classic. Okay. So I want to know your lambdas and your C values. Okay, does that make sense?
Yeah.
Okay, you got the principal result that there's a quadratic relationship between the lambda values and the C values.
Yeah.
Now, it may not, in and of itself, give you exactly the right wavelengths. We might have to fudge.
Okay, that's
By
fine.
a
It's,
certain
I was
per-
just making sure, but I understand what you're saying. If just because it's not the right wavelength, at least
But
all
the
it-
quadratic trend,
it worked
that
out.
quadratic trend, I mean, do you remember when we said we picked the wrong one? And when you pick the right one, it just boom, right along that line with a 99% correlation. It was absolutely magnificent. Do you have your wavelengths for this?
Yeah, I did benzene. I just stopped at benzene because I was doing something else, but I got 538. But I think I did it wrong because I used particle, and I think I used the particle.
Yeah,
in the
you need
box.
to use particle in a ring.
Okay. This is just like chicken scratch of me trying to figure if I'm doing it right, and then I'm going to put it in the lab.
Okay, is there anything
P5.
else that's ticking on the labs here at this point?
I'm good with the labs.
You're good with the labs?
Yeah.
Mhm.
Okay, you mentioned you're starting to encounter some questions on the test.
Yeah.
Do you have that with you or not?
Well, I have the test up here.
Show me real quickly what you're...
Okay, so I'll be starting with this one. So I figure out A, B, and C, but part D is where it says the lab one.
Okay, so what you have to do is differentiate this. Sorry. So the T of X will be minus h bar squared over 2 times the mass of the particle